Hello everyone. Let's solve another Leetcode problem. And today's problem is problem 295, finding median from data stream. So as you know, the definition of a median is the middle value of an ordered integer list. Suppose here is one ordered integer list, 2, 3, 4, sorry. So the median is 3. Uh, and if there are like even number of integers, say 1, 6, 9, 10, in that case, the median is the average of the middle two values. Okay. Okay. So in our problem, we have a median finder class. There are three methods. Median finder. This one initializes the median finder object. Then we have like two other methods. One is the add number. So as you see, this is the data stream. So new numbers are coming, and using add number, we'll be adding that number to our system. And find median actually finds the median of all the values that we have received so far. For example, just I'm giving one example, say uh, I have first initialized the median finder object, and then using the add number, I just add say 1 and then 10, then 13, right? And then after that, in the fourth step, I have this find median call. So the median until now is say 10, right? Find median will give you 10, and then I will keep on adding new numbers, say 6, and then say 9, right? And then I call find median again. So this time you see the middle number is 1, 6, 9. So 9 is the median now, right? 9 is the median, and then I add another number, say 8. Okay, then I call find median again. So this time you see we have like 6 numbers. So if you put them in order array, it will be 1, 6, 8, 9, 10, and 13, right? And the middle two is 8 and 9, and average of that is 8.5, right? So this is exactly what we have to implement. Okay, so let's think about the solution, how we can actually solve this. So far you have understood that we'll be receiving new numbers from from a stream, and using the add, we have to add that number to our system, and then whenever there is a find median call, that should be able to find the median of all the number that we have received from in the stream so far. Okay, so let's think about some naive ways to solve this. First way is like, why can we keep an array list? If we keep an array list, and if an array list is like efficient enough, like if the resizing is great, in that case, the advantage is we can actually add to the array list in order of one time, right? Yeah. So adding to the array list is will be order of 1, right? Okay. And okay, so let's say my stream is 6, 8, 12, and then 1, 5, something like this, right? So it will be 6, 8, 12. So it will be 6, 8, 12, 1, 5, right? So adding is order of 1, but the thing is, if I want to do that find median thing, then first what I have to do is I have to sort this, right? So I have to sort this. It will be 1, 5, 6, 8, 12, right? I have to sort this, and then I know that so far I have like 5 elements. So I can just go to that index 3 and sorry, index 2, or the third element, and find it. So find median will need a sorting. So it will be order of n log n, right? Okay. Now, why can we keep the list sorted all the time? So how can we actually do that? Okay, let's say, so somehow say we keep the list sorted. So next time, so that sort we can call it like using the insertion sort. So this time the only difference is instead of calling the sorting after find median call, we just keep the array sorted all the time. So we use insertion sort. Say we got a new number 2, right, in this stream. So now we have to add 2. So in the previous case, we were adding 2 here, but this time, no. Using the insertion sort, we actually will find the place for 2. So we know the place for 2 is here, right? The second place. To make a place for it, we have to move everything one place to the right, okay? You're moving everything one place to the right and putting it here. Now you can see the add now becomes a little bit costlier. The thing is, to add 2 here, we had to actually move everything. Like we had to move everything one place. So there might be in the worst case in of the items, each of them we have to move one place. So add now becomes order of n, right? But the good thing is the find median, now it becomes super fast. The thing is, we know we have 6 elements. We will keep track of it. And then we know that if we have 6 elements, this is the mid average of the third and fourth element. So the average of that is, so I can just go to the middle and find it. Okay, so using the insertion sort, I can make the find median order of 1. And the space complexity, in both cases is order of. In the first case, it was order of n. Obviously, you see, I am using an array list, but also when we are actually doing the sorting, we may need, so just depending on what kind of sorting we're using. If it's like merge sort with another order of n, quick sort maybe less, order of 1 or order of log n. But overall, the space complexity is order of n. Okay, so depending on whether we have more add operations or more find median operations, we can just either use the array list directly or use insertion sort whenever we are adding. Now let's talk about another method, which I would say is probably the most optimized method for this kind of problem. So why don't we, so we have a stream, right? So why don't we just keep 2 data structures? So that one of them will have like all the smaller half values. So I will try to keep these data structure balanced. So the number of elements in both of these data structures are equal. So all the smaller numbers will go here and all the larger numbers will be here. Okay, and as you see, since this is a stream of numbers, I have to keep on balancing, right? So let's say at some point we have these values 6, 1, 3, 8, and 20, right? Something like this, and then say 30, right? So the larger values like 20, 30, and then 8 will be here, right? And the smaller values, say 1, 3, 6 will be here, okay? Now, what kind of data structures we can choose? One of the best data structures that we can choose is priority queue or heap, right? Or heap. So this is, since we want to keep the larger values here, this is going to be a min heap, and this is going to be a max heap, okay? The benefit is for the max heap, the largest value is always going to be on the top, and for the min heap, the smallest value is going to be on the top, right? Okay, so these things have been added, and somehow for now think that we have balanced the values in such a way so that all the large values go to the min heap, and all the smaller values, the half of this smaller half is in the max heap. Now if someone says find median, then we know that the median is going to be, we have to just add these 2 of the top and then find median becomes like 6 plus 8 divided by 2 equals to 7, right? So the find median is super simple. It will be order of 1. Now adding things, that's the tricky thing. Let's say we have to add, say, okay, so here is one thing. All the time, we may not have like even number of numbers, right? So let's say we are adding, let's say 7, okay? Now the thing is, obviously, we have to like, or instead of 7, let's add this. Let's add 9, okay? So we have to make sure that if there is like odd number of, like the odd number, the odd index has to be added. Like if we have like odd number of elements, in that case, one of the heaps will contain one more element. So in my case, I will keep the mean heap the larger one. That means when there is an imbalance, the new element, like the mean heap, will have one more element. So 9 will go here. Still 8 will be on top. Now the thing is, if I call find median, okay, so how much time it took to add 9? You see the add thing is order of log n. You know from the complexity of the heap, right? Add operation is order of log n. Still 8 will be on top. Now the find median, this time, you see the size of the heaps are not equal, right? We know that this one is larger. So if this is larger, what I can just do is I just go and grab the top of it, and the median is 8, because I know that there are like 3 elements here, right? There are 3 elements here, and then there are 4 elements here. That means the middle element of the stream is here. Okay, now more things that we have to think. Let's add, say, let's add, say, 50, okay? Now the usual thing is, since this is now the number of elements are again becoming even, we obviously want to keep both the heaps same size again, right? But if I add 50 here, that's going to be not right, quite right, because you see 50 actually belongs here, right? Okay, so to make things right, we know that we have to add it here, but that will actually make the heaps imbalanced, so we cannot just find median easily. So what we do in that case is, right, whenever there is whenever we know that we have to add here, instead of adding here directly, first we'll add, say, here. Okay, we'll add here, and next what we are going to do is we are going to take out the smallest element and add it back here. Okay, so the smallest element is 8. We just will take it out and add it here. And 9 will actually now go on top of this. That's a simple thing that we can follow. That means whenever we know that we have to add something here, instead of adding to the max heap, we first add it to the min heap, and then pull the top element and add it to the max heap. So that way, I'm making sure that I am adding one element to the max heap, but at the same time, both the heaps are balanced, right? Okay. Now let's add another thing. Let's say adding 2, right? This time we know that again we are having the odd element. Sorry, the odd number of elements. So from our policy, we are actually we want the mean heap always larger. But the thing is, you can actually have your own policy and keep the max heap larger. But if I am keeping the mean heap larger, but the thing is, you see that I know that I want to add it here because already these two heaps are like same size. So the new element I want to add to the mean heap, but you see 2 actually doesn't belong here. 2 actually belongs to the other heap. So just like the previous case, I know that I have to add here. So whenever I have to add to the min heap, I just go and add it first to the max heap. Okay. And then what I do is, okay, so this time actually the max heap had, like, sorry, 6 was here and 8 was here. Okay, so I am adding 2 here, and then I take the this thing out and add it to the min heap. So that means I take 8 out and add to the min heap. Now there will be change in both the heaps, so 9 will come here and 8 will go here. And in this heap, 2 is going to be here. Sorry, 6 is going to be here. 2 is still here. Okay. So the same thing, just to keep the heaps balanced, whenever I have to add to the max heap, I just, instead of that, I add the value to the min heap, and then take the top value and add it to the max heap. Similarly, if I need to add to the min heap, I just first add the value to the max heap, and then take the top value or the largest value from the max heap and add it to the min heap. So that's it. As you can see, the find median is now so easy. It's order of 1. And at the same time, the add thing is also order of log n, which is better than the previous case, right? In the previous case, if I wanted to make the find median order of 1, it was order of n add thing. But if I wanted to keep the, so this time it's like, if I have heap, this one becomes add becomes order of log n, and find median becomes order of 1. Okay. And the space is obviously, I am keeping everything in the heap, so it's order of n. So let's go and check the code. So we had a priority queue min heap, and then another priority queue for the max heap. The default priority queue in Java is min heap, so we change the parameter to collections dot reversed order to make it a max heap. Okay, so the max heap will have the smaller numbers, and the min heap is going to have the larger numbers. And then this is the add thing. You see, whenever we are adding, we're seeing if the min heap size is equal to the max heap size, right? In that case, we want to add to the min heap, right? So instead of adding to the min heap, first we add the number to the max heap, just I showed you in the example, and then take the top of the max heap and add it to the min heap, right? Okay, so that was the case if the 2 heaps are already equal. But if the 2 heaps are not equal, that means obviously the max heap has 1 less element. We want to add the 1 element to the max heap. We want to add 1 element to the max heap, but instead of adding to the max heap directly, we first add to the min heap, and then take off the min heap and add to the max heap. So you know why we're doing this, right? And then the find median method, we're seeing, we'll check if the 2 heaps are equal. We know if the 2 heaps are equal in size. In that case, we have to take the top of those 2 heaps and then divide it by 2. Otherwise, if the 2 heaps are not equal, I'm keeping the min heap larger. So I just take the pick top of the min heap. Okay, so that's it. Thank you very much for watching. We will come back with another problem next time.